Welcome to the new era of video creation with Bayozi. This is our new series on teaching deep learning. Today, we will discuss self-supervised learning. Here are the contents. Self-supervised learning, SSL, is a paradigm in machine learning where a model learns from unlabeled data by creating its own labels. This contrasts sharply with supervised learning, where labeled data is required for training. SSL leverages the inherent structure in the data to generate pseudo-labels for training. These pseudo-labels allow the model to learn meaningful representations or features without needing manual annotations. SSL provides a middle ground between supervised and unsupervised learning. It doesn't rely on labeled data like supervised learning, nor does it completely forgo labels as unsupervised learning does. Instead, it generates labels by predicting parts of the data from other parts. This method allows the model to learn patterns that can later be transferred to specific tasks, such as classification, regression, or object detection. In practical terms, SSL is becoming increasingly crucial due to the scarcity of labeled data in many domains, and it enables scalable learning from vast amounts of unlabeled data. One of the significant challenges in machine learning is the reliance on labeled data. Labeling data, especially in specialized fields such as medical diagnostics or autonomous driving, is both expensive and time-consuming. In many cases, collecting a sufficiently large and diverse labeled dataset is simply impractical. This is where self-supervised learning, SSL, becomes invaluable. By enabling the model to learn from unlabeled data, SSL alleviates the burden of manual annotation. With SSL, models can leverage massive amounts of raw, unlabeled data, which is often much more abundant, thereby sidestepping the need for extensive labeling. In fields like natural language processing, NLP, or computer vision, SSL has shown tremendous promise, allowing models to learn generalizable features that can be later fine-tuned for specific tasks. The ability to handle large datasets without explicit labels makes SSL a powerful tool for real-world applications across many domains. In supervised learning, models are trained using labeled data, where each input has an associated output label. This approach is effective when labeled data is available, and the task at hand is clear. However, supervised learning relies heavily on the availability of high-quality labeled data, which is often costly to obtain. In contrast, self-supervised learning does not require labeled data. Instead, the model generates its own supervision through pretext tasks, where it learns to predict parts of the data from other parts. For instance, in image recognition, a model can be trained to predict missing patches of an image or the relative position of image segments. This allows SSL to make use of large volumes of unlabeled data, a critical advantage when labeled datasets are sparse or expensive to curate. SSL models can then be fine-tuned on smaller labeled datasets to perform specific tasks like classification or regression, making them much more adaptable and cost-effective than traditional supervised learning approaches. At the core of self-supervised learning are pretext tasks where the model generates its own supervision. These tasks do not require any labeled data. Instead, they leverage the structure or inherent properties of the data. A pretext task can be as simple as predicting missing parts of an input, such as predicting a word in a sentence, or predicting the color of a pixel in an image. The model is tasked with learning useful features to solve these pretext tasks. There are two main approaches in SSL: contrastive learning and generative learning. In contrastive learning, the model learns to distinguish between similar and dissimilar pairs of data points, e.g., learning that two augmentations of the same image should be close in feature space. In generative learning, the model tries to generate missing parts of the data, e.g., filling in missing words in a sentence. Both approaches allow the model to learn powerful data representations that can later be applied to specific downstream tasks. By creating pseudo-labels through these methods, SSL enables models to use vast amounts of unlabeled data to learn without direct human supervision. Contrastive learning is a self-supervised learning technique that focuses on learning by comparison. In this approach, the model is trained to distinguish between similar, positive pairs of data points and dissimilar, negative pairs. For instance, In the case of image recognition, the model may be shown an image and its various augmentations, e.g., cropped, rotated versions, and the task is to learn that these different augmentations represent the same underlying object. Conversely, the model learns to differentiate between images of different objects. Popular frameworks for contrastive learning include SimCLR and MoCo. One of the core challenges in contrastive learning is negative sampling, the task of selecting dissimilar pairs from the dataset to encourage the model to learn meaningful differences. This process is computationally expensive but critical for training robust models. Despite this challenge, contrastive learning has been highly successful in producing transferable representations that can be fine-tuned for tasks like image classification or object detection. In generative self-supervised learning, the goal is to reconstruct or generate missing parts of the input data. This approach is driven by the intuition that if the model can learn to predict or regenerate parts of an input, it will have learned useful features about the structure of the data. An example of a generative pretext task is autoencoders, where the model compresses input data into a latent space and then reconstructs it. Generative adversarial networks, GANs, are also used in SSL, where the generator learns to produce realistic data samples, and the discriminator distinguishes between real and generated data. These methods are particularly useful for tasks like image completion or text generation, where the model must predict missing elements. Generative SSL methods allow the model to develop deep knowledge of the data's distribution, which can be applied to tasks such as data augmentation, image synthesis, or language modeling. Self-supervised learning has made a substantial impact in natural language processing, NLP, particularly through language model pre-training. Methods like BERT and GPT use SSL techniques like masked language modeling, where a portion of the words in a sentence are masked, and the model is tasked with predicting the missing words. This pre-training allows the model to capture rich semantic and syntactic representations of language. The learned representations can then be fine-tuned for specific tasks, such as sentiment analysis, machine translation, or text classification. This transfer learning capability is a hallmark of SSL, where a model trained on vast amounts of unlabeled text can be adapted to a wide range of specific tasks with relatively small labeled datasets. SSL has dramatically reduced the need for large amounts of task-specific labeled data in NLP and has set new standards for state-of-the-art performance in language understanding. In computer vision, SSL has gained widespread use due to its ability to leverage large quantities of unlabeled image data. In traditional supervised learning, obtaining labeled datasets for image classification or object detection can be expensive and time-consuming. SSL techniques, especially contrastive learning, have been successfully applied to learn rich representations of images from unlabeled datasets. Methods like SimCLR and MoCo use data augmentation, e.g., cropping, flipping, rotation, to create positive pairs, while negative samples are drawn from different images. These representations can then be used for a wide range of downstream tasks like object detection, semantic segmentation, and even image retrieval. SSL has proven particularly effective in vision tasks where large labeled datasets are hard to come by, making it an essential tool in modern computer vision applications. In the domain of speech recognition, SSL has been highly effective, particularly in dealing with unlabeled audio data. Speech data, such as recordings of conversations or natural speech, is often not labeled or manually transcribed, making it a valuable resource for SSL. One common pretext task in speech modeling is to predict missing or corrupted parts of audio sequences, forcing the model to learn the temporal patterns and structure of speech. Self-supervised models such as WAVI2VEC 2.0 and VQVAE have been trained using SSL to learn powerful representations of speech signals. Once these models are pre-trained on large amounts of unlabeled speech data, they can be fine-tuned for specific tasks like speech-to-text, speaker identification, or language understanding, even when labeled data is scarce. The most significant advantage of self-supervised learning is its reduced reliance on labeled data. SSL models can learn from vast amounts of unlabeled data, which is often much more abundant and less costly to acquire. This capability is especially valuable in fields like healthcare, autonomous vehicles, or rare event prediction, where labeled data is expensive or difficult to obtain. SSL also offers scalability, as models can learn from large datasets without the need for manually labeled examples. Furthermore, SSL is flexible across domains, including image, text, and audio, making it applicable to a broad range of applications. Perhaps one of the most compelling aspects of SSL is the transferability of learned representations. Models pre-trained with SSL can be fine-tuned on smaller labeled datasets and still achieve high performance on a wide variety of downstream tasks. While self-supervised learning offers significant advantages, there are several challenges that researchers and practitioners face. One of the primary difficulties is designing effective pretext tasks. The task must be challenging enough to encourage the model to learn rich and meaningful features, but not so complex that it hinders learning. There is also a need for substantial computational resources to train SSL models, especially when working with large datasets and complex architectures like transformers. Evaluating the quality of the learned representations is another challenge, since there is no clear ground truth as in supervised learning. Lastly, there is a trade-off between the complexity of the pretext task and the simplicity of the model. Striking the right balance is crucial for making SSL both effective and efficient. Recent advances in self-supervised learning have led to dramatic improvements in performance and applicability. In natural language processing, transformer-based models like BERT, GPT, and Roberta have been further refined, allowing for better pre-training strategies. These advancements are pushing the boundaries of SSL, making it an even more powerful tool for training models across different domains. In the field of healthcare, self-supervised learning has significant potential, particularly in the context of medical imaging. Annotating medical images such as X-rays or MRIs is often time-consuming and requires expert knowledge. SSL allows the model to learn from large collections of unlabeled images, leveraging pretext tasks like image inpainting or rotation prediction. These representations can then be fine-tuned for specific tasks like disease detection. Similarly, SSL can be applied to electronic health records, EHRs, where patient data is often unlabeled. By learning useful representations from these records, SSL can improve disease prediction and diagnosis, even when only a small subset of the data is labeled. This ability to handle limited labeled data in the healthcare domain is a crucial advantage. The future of self-supervised learning is incredibly promising, with several exciting avenues of research. One major direction is improving pretext tasks. Researchers are working on more effective and sophisticated tasks that can lead to better generalization across domains. Cross-modal learning, where models learn from multiple data types, e.g. both vision and text, is another area of growing interest. SSL could enable models to learn from multimodal data more effectively, allowing for better multimodal representation learning. Additionally, SSL is increasingly being integrated into reinforcement learning tasks, where agents can learn from unlabeled interactions with the environment. Finally, the combination of SSL with transfer learning is likely to lead to models that can efficiently transfer knowledge from one domain to another, making SSL even more versatile and powerful. In conclusion, self-supervised learning offers a powerful approach to learning from unlabeled data, allowing models to generalize and transfer knowledge across a variety of domains. From NLP and computer vision to speech recognition and healthcare, SSL is revolutionizing how we approach machine learning by making it more scalable and cost-effective. While challenges remain, especially in designing pretext tasks and evaluating learned representations, the advances in SSL techniques are rapidly improving its effectiveness. The future of SSL is bright, with the potential for further breakthroughs that will help machines learn more efficiently and with less reliance on expensive labeled data.